So DMA controller is there, and so we'll be making a utilization of DMA controller. Coming back, we were making a discussion on direct memory accesses. So the thing is, if you are making a consideration of a device like a disk, where if suppose a lot of data is supposed to get transferred in kilobytes, the transferring of data, it is supposed to take place, and this is something which is supposed to take place in a disk, so it will take a lot of time. So for every block of data, if you are thinking of generation of interrupt, a lot of CPU cycles will get wasted. So despite of doing the thing in that way, we are making a utilization of direct memory access approach. In direct memory access approach, direct the IO devices, they are given the mm, uh, direct interfacing with the IO devices. Directly the interaction, it could go to the IO devices via the memory, the system buses, they are offered to the IO devices. So for having that, the DMA controller is there, and these DMA controller, they are interfacing with the IO devices. The IO devices, they are making request, the DRQ request is there, then DMA controller, it is forwarding it to the processor. The processor will be making an acknowledgement of that, and then the DMA controller will be telling the IO device whether the IO device, it can make a utilization of the buses, and these buses, there is something that is called hold, and there is something that is called HLDA. So DMA controller is something which is going to place the hold, is something which it will be making a request for holding the channels, and HLDA is something which is going to get acknowledged via the processor. The HLDA activation is something which will make the IO device to make a utilization of the buses. So HLDA activation, and then HLDA activation will proceed with DAC activation. So when these two activations, they are there, then in that case the IO device, they are able to make a utilization of the system buses, the memory bus, that is the control bus, data bus, and address bus, and then things, they are appearing now. Seeing to how in terms of steps, how things, they are taking place. So in step number 1, IO bus device request DMA using INTR through DMAC. So IO device, it is making a request, and then through INTR, it is going to the processor. Then in step number 2, processor initiates DMA control register, so it will be seeing, so control logic is there in the DMA, it will be making a check on that, and DMAC initiates a DMA transfer, so it initiates a DMA transfer by means of hold, and then HLDA is going to get informed, and then in step number 3, IO device transfers data directly using IO and memory bus through DMAC, hold, and HLDA. As I told you, that HLDA activation and DAC activation will enable the IO device in transferring the data. So in step number 3, that is what is specified. IO device transfers data directly using IO and memory buses. So by making a utilization of the IO buses, which are interfaced with the DMAC, and hold and HLDA functioning as control signals. So hold and HLDA are functioning as control signals. So IO device transfers data directly using IO and memory buses through DMAC, hold, and HLDA functioning as control signals. So things they are going, and then in step number 4, IO device requests interrupt through DMAC logic when DMA done. So when the IO device it is able to complete its operation, then it will be telling the 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 DMAC, that is direct memory access controller, that it is able to complete the operation. Then DMA controller will be informing the processor that the operation that which was intended out of the IO device, it is able to finish the operation. So it will be informed to the processor. So DMA is something which is done in this way. Another figure is there which specifies of the same thing. So CPU is there, and then I told you about the address count and control. This figure also speaks of the same thing. So here it is speaking of the same thing. So CPU program is program the DMA controller. So CPU program is there which makes a call to the DMA controller, because this call is for an IO device, that is the disk. So from here it goes, the DMA request is transferred to the memory, that is now it goes to the disk controller, and a disk controller now disk controller is there, and you may see the drive. So and then what happens, the data it gets transferred to the main memory, because this is something DMA transfer is something which gives a privilege where the IO device it is having direct access to the memory. So this is what is specified. So data transferred, and after the data it gets transferred, then the interrupt it goes, and this is the bus. So interrupt it goes, that the work is being done. So when the things they are completed, then interrupt done, then the CPU it is informed. Then coming to the next topic, that is IO buffering. IO buffering is the next topic. So IO buffering, in IO buffering the concept is, now think of a user process, and this user process it is wanting something out of an IO device, some read or write operation it is supposed to perform on an IO device. So the first case is where no buffering is there. Then in that case, think of a case where a set of characters it is supposed to come out of an IO device. Then in that case, what will happen? After the passing of each and every character, the process it is going to get interrupted. So a lot of cycles will get wasted. So one character is there. So what will happen? The process it made a request to an IO device for a set of characters. So this after the request it will get blocked, and when the one character is available at the device end, and this character it gets transferred, this will this process will get unblocked. One character is there, but the operation it is yet not completed, so it will be making a request for the next character, and it will get blocked. So again and again and again, this is something which is an inefficient approach. Again and again you are getting interrupted, you are getting blocked, things they are appearing, and the second approach is single buffering approach. In single buffering approach, there are now here in this case interruption is something which is taking place every now and then. The process it is getting blocked, and then it is waiting for the next character to come. And beside of having this, what we can do is, in the user area we can think of a buffer, and the data it could go onto that buffer. But again, in this case again, this approach it could be facing some problem. What the problem would be, now you can think of a phenomena. Now this buffer it is going to be in the user area, so there is going to be a page where the buffer it could be there, and things they are getting onto that page. Think of a case where this page it swaps out, so it is not there. In that case, a problem would be there. So what you can do is, you can think of a case where you will be locking the page, and you will not be allowing the page to go out of the scene. But this is something which is again not achievable, because a number of processes, think of a multi-programming environment, a number of processes are there, and if locking of the pages for buffering it is going to go, the number of pages, there will be a shrink in the number of pages, the number of pages availability it will go down. So you cannot go with this approach. The approach is, you can think of a space in the kernel area which is which is serving the purpose of a buffer. So a buffer it could be there, the IO device it is placing the characters. So when all the characters they go onto the buffer, the interrupt it could go, and things they could go in that way. But again, in this approach there is a problem. What the problem is, now what we are thinking of is, the page it is going to go out of the memory, and then think of a case where the place where the data it is supposed to go, it was paged out, and then again the page it was arriving in. So arrived in, but the place is not empty. So the data it is there in the buffer, but the data it could not go into the user area, because the area it is already filled. So what you can think of is, single buffering it reduces the pain. What it was there in the earlier approach, in no buffering, what the pain it was there, single buffering it reduces the pain. But again, the problem which I just specified, the area on which the data it is supposed to go, it is already filled. You are having the data, but it could not go in that area. So what we are thinking of is two buffers. So in one buffer we'll be placing the data. As and when the data it will be demanded by the process, it is going to move, and there is another buffer where when the availability of the data is there, you will be placing the data onto the buffer. So two buffers are there, and by making of a utilization of the two buffers, what problem we were facing in single buffering is somewhat reduced. But the buffer mechanism that which is utilized nowadays is the circular buffering, where we are having multiple buffers, and the implementation is somewhat similar to what we already made a discussion in the producer consumer problem, where we were having the pointers. There was a pointer which was addressing to the first location which was having data in it, and another pointer was there that was pointing to the first free buffer location. So by making a utilization of those two pointers, the producer consumer problem that we made a discussion of, that framework it could be utilized for implementation, and this framework is something that which you might be seeing in several implementations of operating system where buffer implementation it is taking place. So all these four approaches are there. Then we'll be having a discussion on the last topic in the current discussion. So the last topic in current discussion is uh, the uh, the model, uh, the design issues, the operating system design issues. So operating system design issue in the context of the IO devices. So when you are thinking of designing of the framework that which it could be able to make the best out of the IO devices, designing an IO devices and to have the best out of it. So there are various features that which you will be interested in. So the designing of the IO device, there could be several objectives, but out of those objectives there are two factors on which the designers they majorly focus on, and the two factors are efficiency and the second factor is generality. So speaking on efficiency, now we all know that there is a big gap, there is a big speed gap between the IO devices and the various the other two devices, that is the two major other components present in the computer system, that is processor and memory. So efficiency is something that which the designer of the IO devices they are largely interested in. They would be thinking of having something where this gap that which is there between the speed of the processor and memory, it goes down. Uh, so majorly when you will be making a discussion of the IO devices, the majority part it goes to the disk, because the disk is something which is an IO device, and for performing a variety of operation it is heavily utilized. So when you will be thinking of the operating system designers designing the IO devices, they are majorly interested in disk, although there are various other devices also, but disk is something which is heavily discussed. Then the second factor uh, which I just specified, on which the IO designers they may be interested in, is the generality factor, where the idea would be to have interfaces which are simple in nature, and error handling is what is supposed to take place. So this error handling, the approach is going to be somewhat you are handling the various IO devices in a similar way, although this is something which is very hard to achieve, because the complexities that are associated with the IO devices, the applications that they are meant for, there is a big variation. So having something that which is same, that is handling each and every device in a similar way, is something which is very difficult to have, but the operating system designers they try to have something which is going to make a consideration of all the devices in a similar way, although the complexities of the various devices it varies, and it is because of the complexities and the application demand that which we are seeking out of the various IO devices, we are having a difference in implementation in terms of generality. So coming back, so what operating system designers they do is they form levels. So various IO devices are there, and depending upon what nature they actually portray, layering is something that which is happening. The problem that which the IO device it is supposed to portray, sub problems, the problem sub problems, they are identified in the problem domain, and then we are forming layers where the layer beneath is providing services to the layer upwards. And then if you see the layers, and if you see what is happening from the topmost layer to the bottom layer is there is a speed association is there. So when you go from top to bottom, the time that which is associated with each and every layer, it goes down. So the lowermost layer, it is going to have the least time span, and the top layers, they are going to have larger time spans. So a local peripheral device, it is going to have an organization of this sort. A communication device, it is going to have an organization of this sort. A file system, it is going to have an organization of this sort. So making a discussion on each of these organizations separately. So first of all, make a discussion of on this, that is local peripheral device. So in first layer we are having user processes, in second layer we are having logical IO, in third layer we are having device IO, in fourth layer we are having scheduling and control, in fifth layer we are having hardware. So user processes, the second layer is logical IO. What logical IO layer will do is, so logical IO layer, it will consider the resources in terms of logical resources. It will make a consideration of the IO device as a logical resource, and at this layer the idea would be what the operations the device it is intending to perform. So at the logical level we will be fixing that also. So we'll be trying to identify, so identifiers are something that which will be associated with the resources, the IO devices. We'll be associating identifiers with them. We'll be thinking of the resources as logical devices. We'll be trying to find out what operation it is intended out of the IO device, and at the logical level in this layer, that is what we'll be doing. And then we are having device IO. So in the previous layer we were able to fix out what the operation the device it is intended for. So in device IO we will be organizing the set of instructions which must be executed on behalf of the operation which the device it is supposed to perform. So we will be making an organization of the instruction. Not only this, buffering is something, buffering concepts and all those concepts, the implementation, it goes in the device IO layer. Then comes the next layer, that is scheduling and control layer. So actual queuing of the request onto the device is something which is going to take place in this layer, and this layer is something which is in direct interaction with the hardware. So this layer, it makes a utilization of the hardware and performs the necessary activities on the hardware, and then after performing the activities, the results, they are forwarded up to the user process level. So local peripheral device, this is how the breakage of how the organization of the functionalities it takes place. Now in the same system for the different devices, this is how it may go depending upon the class to which the device it actually represent. If the device it is a local peripheral device, then you can go with this organization. If it is a communication device, you can go with this organization. For file system, you can go with this organization. So making a discussion on the second organization, user processes, it remains the same. Communication architecture is there. So communication architecture, again in communication architecture you may be seeing the set of layers. Again, a breakage it could be there. You can make a consideration of TCP IP layering. So again further breakage is there, and then the rest of the layers are same as that of local peripheral device. So I will not be making a discussion on them. Communication architecture, again TCP IP, some layering is something, again further breakage of this into layers it could take place. Then the last one, user processes, then directory management. In this layer what is going to be done is, now when you are making a reference to a file, the reference to a file it is symbolic in nature. So we are basically making a conversion of symbolic references into the form of identifiers, and we'll be making a utilization of the file descriptors and the index tables for identification of the identifiers. File identifiers are supposed to the conversion that is supposed to take place from symbolic reference to file identifiers. So and at this level we'll be making a modification in the directory structure, like adding, deleting, all those things they will take place in this layer. Then the second layer is the file system layer, where we'll be thinking of the operations that are going to get performed on the file, like open operation, it could be there, close operation, read, write, what all operations they are intended on the file. So in this layer, that is what is going to get fixed. And then if we are having the physical organization now, we all know that we already had a discussion on that. When you are thinking of a virtual memory, then logical to physical translation is something which is supposed to take place. Now here, when you are making a consideration of a file system, then also the transformation it has to take place. So blocks of data are there which are there in the disk, and you are supposed to locate them. So logical to actual physical transformation is something which is done, which is going to be done in physical organization. Then device IO is something which is same as the previous two approaches. Scheduling and control is something that which is same as the previous two approaches. So at this point we are closing the current discussion. So this completes what all things we had a discussion in the current lecture, in the current of 4 or 5 videos we made on the IO devices. In that we had a discussion on introduction to IO devices we had, where we were able to explore what are the classes in which we can make a classification of the IO devices: human readable, then machine readable, then communication, then what all different parameters are there.